All right, everyone. So welcome to the last little bit of the day before we get to our um, weekend and actually have a break for a few days. Um, so hopefully you'll last through the last 2 hours and then we can actually relax. So what have we been up to? So right now we were saying, well, last time we were saying that there are basically three things because the hierarchy problem or electroweak hierarchy problem is actually at the stage where it's very sensitive, um, hierarchy, whatever. Um, you'd think working on a problem makes me know how to spell it. Apparently not. Okay, so the statement is we're really at a place where their details matter. So there are basically three things to really get. One is order one numbers are important. We are not at the stage, let's say like the cosmological constant, where you're like 15 orders of magnitude off. Here, getting a factor of 2 could actually go from not being excluded to excluded. So the whole point here is, how can we get things in our favor? How to get in favor, in particular, in our favor, and in particular, how to get slightly smaller order 1 numbers than you might expect, right? Rather than being a loop factor, how do you get like a half times a loop factor, or maybe 2 loop factors, or things like that. The second was, people often assume that the scale you estimate with dimensional analysis implies particles. And the question is how easy it is to see these particles and whether or not these are even particles to begin with. And then finally, what we spent the most time on so far still has been evading dimensional analysis. Okay, so last time we were talking a bit about order 1 numbers. And what were the two things we got to? One was, case 1 was extra dimensions, which basically gave us a factor of 1/5. This gave us order 1 number is the same as, let's say, supersymmetry times 0.2 roughly. So great way to evade current constraints if you can keep that factor of 0.2. Next, we did NEMA's G minus 2, where there, what we saw was actually you got the result times an extra loop factor. So this is a normal, quote unquote normal. And we gained an extra loop factor just because there were extra cancellations that happened when you UV completed the theory. So what we're going to continue doing is just finding more examples. And you can ask, why am I doing all this? I'm basically giving toy examples where 1 and 2 are being realized. Obviously, the next step would be to take any of these things that you might like and actually incorporating them into some theory of the Higgs mass, so putting the standard model in them. This has not really been done entirely yet. So this is more just showing the philosophy behind everything. There are counterexamples. The next step is, of course, just putting the standard model into all of this. And so for everything I'm going to be talking about here, there's quite a bit of opportunities because people haven't taken any of the ideas I'm going to be talking about and married them with the standard model yet. Okay. Another way, so 3, let's go through again. Let's now start talking about how you can be parametrically wrong. So not just getting order 1 number, but you're getting the scaling wrong. So let's see how we can get some examples where the scaling of our estimate is wrong. Okay, so the easiest way to sort of get scalings wrong is to use discrete symmetries. So we're going to be talking about two models that have a Zn symmetry. And in fact, we've sort of already seen a model where the scaling goes wrong in the form of the relaxation model. We just didn't really talk about it much. So let's make this a bit more explicit again. So let's say, like before, we are going to have a spurion. I'm going to say it's kappa instead of kappa squared this time. E to the I alpha phi over f. There's a phi over f. Let's put a minus sign. And let's see. So this is the spurion, and then we're going to write a Zn symmetry again. And under Zn, so this is the spurion. Zn, we're going to again do phi over f plus 2 pi over n. And let's write a theory coupling this to a fermion. So we're going to have m fermion psi bar psi. We're going to have a dimension 1 guy coupling to it. So this plus its Hermitian conjugate again. Ti phi over f psi bar psi plus complex conjugate. So this is secretly m plus kappa cosine phi over f. I'm going to be blasé about the phase. We're going to have to make this Zn symmetric. So 1 plus kappa cosine phi over f plus 2 pi over n psi 2 bar psi 2 plus dot 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 n times. Right? And so at this point, we're just going to do a calculation, or in fact, we're not going to need to do the calculation, but we can just calculate what is the mass generated for this scalar phi. Whoops. So in particular, what are we going to do? We're going to integrate out the fermions and see what is the mass. Okay. Integrate out fermions. And rather than going through the calculation, it's messy, right? You take V Coleman-Weinberg for a single guy, for the m of the ith guy, and you sum over I. This is the total thing, at least at one loop, let's say. But we can just do the whole thing of, let's just Taylor expand this, Taylor series, and just see what can we write down. And so what are we going to Taylor series in? We cannot Taylor series in K, right? You cannot do a Taylor series in dimensionful parameters. No dimensionful parameter is ever small. Only dimensionless guys are ever small. And so we're going to pull out a mass term here. So this is the m of the fermion is, pull out an m, 1 plus kappa over m times the cosine of phi. And here's our small dimensionless number that we can Taylor series in. Okay, so we're going to go back to the argument we had before on why things are small. I want to write something here that is invariant under all my symmetries. And the statement is, well, you can't do it unless you do kappa over m to the nth power cosine n phi over f. Right? You need to be cosine n phi over f, n here so that it's invariant under this Zn symmetry. And then every frequency of phi comes with kappa over m here, and then we can just say m to the fourth times something. So what do we have? We just talk about parametric scalings. Taylor series this guy, m phi squared is of order m to the fourth, kappa over m to the n, and then two derivatives gives an n squared over f squared. So this is the parametric scaling of the mass. And let's compare this to the normal dimensional analysis argument, which we do not knowing that we have a Zn symmetry. So you can ask, what actually went wrong with dimensional analysis? Nothing ever goes wrong with dimensional analysis. You can sometimes misuse it by not putting in all the symmetries of the problem. And so remember we had said scale, which is, let's say, roughly m of particles, is roughly m phi over y. So you see like the mass of the fermions are all of order m. And so we would have guessed up to order 1 numbers that m phi is y times this m parameter. Right? Let's take kappa small so that we're not even changing the mass of the fermions by very much. Okay, what is the Yukawa coupling? Taylor series this. This is roughly kappa over y, order 1 number, phi times psi bar psi. And so this is our Yukawa. That's F. Did I use capital F or I lose little f? Okay. So this is what we think the Yukawa, we can just measure the Yukawa coupling. And let's see what the mass scales as then. We actually calculated the mass, m phi squared, or we have an expression for linear in phi, so let's take the square root. There is a m times m over f. There is a kappa over m to the n over 2. So if this thing just happens to be something like 0.1, I can make the mass here, m of the scalar, to be exponentially lighter than you would have thought here, right? Or in this estimate. This estimate is just like, it's mass of that guy times whatever your Yukawa is. My Yukawa has 1k here, but notice that there n over 2k's there. So you can get an exponentially lighter scalar than you would have otherwise thought. So what is this saying? Basically, this is just saying that if you miss a symmetry, you can very badly misestimate the size or do dimensional analysis wrong. And symmetries here, notice exchange particles which have different masses. This is just like the NEMA G-2, but on steroids, right? There you are off by a loop factor. Here, I can just set n to 100 and be off by like 10 to the minus 100. Like I can make myself as wrong as I want to be here. So, moral of the story, if you discover stuff, let's say you discover this, but you haven't discovered these other guys, you could very easily just be getting the wrong answer. Okay, so this is an example where you can get parametrically the wrong answer. Let's look at another example of getting parametrically the wrong answer. This one will also be Zn symmetry there. Okay, so let's write an easy potential and an easy UV completion. So let's say my potential has just a real scalar, 1/2 m squared phi squared plus lambda phi to the 4th, right? And I can ask, what would dimensional analysis guess where the scale of new physics is? The scale, scale, which we decide to associate is m over square root of the quartic. So if you go through the dimensional analysis argument I sort of detailed before, well, God, maybe in the first lecture, this is actually how it looks. And if we decide to say, so here what we're going to do is we're going to show scale is not equal to m new particle. So what we'll see is actually you do dimensionally guess something important, but it has nothing to do with the mass of a new particle. And it turns out to be quite easy to see. So what we're going to do is write down, say, okay, you discovered a mass term, a quartic term. Let's say you just continue to experimentally probe the system. You discover higher order terms. And you discover that the potential is V equals some number, let's call it epsilon to the fourth, cosine phi over f. Okay. Notice this is saying the scale that you're guessing here is the mass term, which is epsilon to the fourth squared over f, divided by the quartic coupling, which is epsilon squared over f squared, is of order f. So we're guessing something happens at the scale f, and very much you can see that, well, the scale f is important here, but the standard thing is saying that new particles appear here. So let's see, do new particles appear at the scale f? And I'm going to do it by just writing down a UV completion for which new particles appear at a scale much larger than f. So it's going to be just do this all by examples. Let's say this is very Goldstone boson-like. So we're going to write down a theory that has V equals minus 1/2 m squared phi squared. I guess m can be some real guy. Plus quartic coupling of phi to the fourth. So this gives a nice Goldstone boson. And we're gonna, as before, write a Zn symmetry under which phi goes to phi e to the 2 pi I over n. So I can say, actually, this theory is not a U1 spontaneously broken. There's a Zn symmetry, so eventually I can get a mass to the Goldstone boson by writing phi to the n over whatever, let's say m Planck to the n minus 4. So what do we do? This gets a VEV, standard Goldstone boson. I'm going to call it VEV capital F plus the radial mode of x e to the I phi of x over capital F here. So here's my Goldstone boson. Phi, radial mode F rho, where I'm just going to set this equal to 1. So there's one scale in the problem. Capital F equals capital M equals mass of this new Higgs mode, this rho. Right? There might be 2's, square root of 2's, whatever. But there's one scale in this problem. That's the mass. And then the Goldstone boson is massless until we take into account this guy here. And let's just plug this in. What do we get? Okay, we get a term that is capital F to the n, m Planck to the n minus 4, cosine n phi over capital F, right? So I just plugged everything in here. Notice the exponential gets to the nth power. So we can identify it with our theory by just saying capital F over n is equal to little f. And so what do we see? We see the scale we get from dimensional analysis. is little f, but the mass of a new particle, m rho, is capital F, which we had said is n times f. And so we can just take n larger and larger and separate this much larger than f. Okay, so maybe the simplest example I know of where you can just show that dimensional analysis, the typical arguments, give you a scale. The scale is important, right? You see, go to field values of f, and you start seeing this thing as cyclic rather than just a m squared phi squared plus phi to the fourth term. But it has nothing to do with the masses of new particles. So this is sort of just an example of if you're trying to do dimensional analysis, what you get out might not be the mass of a new particle. In this case, it's, in some sense, it's a little more like you guess the field value where some stuff happens. So, yeah, so a simple example. Okay, let's see. Do I want to go more? I guess I could. Any questions so far, or? Hopefully I'm not going too fast for people. Okay, so last time we sort of said order 1 numbers could be completely different than really are order 1 numbers. We can't guess it. Here we're saying the scale you're estimating may not be the scale like the mass of a particle. So let's ask, in particular, this example seems like it's saying you can parametrically separate the mass of a new particle than it's from what you might dimensionally estimate. And so let's go through a little bit more carefully in a model like this. Does anything special happen at the scale f? And the answer is yes. The scale f is not just special because it appears in the cosine, but there is other dynamics that appears at the scale f. It's just not what you would have, it's not new particles. So how do I want to do this? It's somewhat easier actually in the case of doing a Yukawa coupling. So I'm gonna actually, the same thing happens in this theory. I'm just gonna, it's slightly easier to write for a theory with a Higgs, with a Yukawa coupling. So let's write, find sine phi over f psi bar psi. And we're going to do is let's just calculate the mass for phi. Calculate mass. Your first statement should be, well, I can only calculate the mass if this integral is finite, right? Otherwise, I need counter terms, and then the mass is not a calculable quantity. And, well, we all know that this integral, phi, right, you just Taylor series this. This integral is divergent, right? It's an integral d4p over I over p slash squared. And we had said this is clearly UV divergent. And so this is not finite. So in other words, it depends on regulators. It depends on all sorts of crap. So you'd be like, well, okay, fine. This mass is not calculable, right? The Coleman-Weinberg term has an mf squared UV cutoff squared. And so clearly there are pieces of this thing that it also has a log, right? Plus mf to the fourth log lambda. And so clearly it's divergent. Crap is happening. You're asking a bad question. But let's be a little more careful. So the claim is, just by writing sine phi over f, this integral is actually now going to be a finite thing. And so let's see what happens. So let's do the Coleman-Weinberg calculation. But you'll notice, so what is the normal Coleman-Weinberg calculation? Coleman-Weinberg, they do this. The potential V is just an integral of a fermion loop, right? Maybe you do mass insertions and things like that, but this is what it is. Okay, but you'll notice this calculation, let's say you can start putting in scalar propagators and things like that. And this does not respect all the symmetries. Doesn't respect phi over f equals phi over f plus 2 pi, right? When I Taylor series the sign there, I am destroying the symmetries of my problem. And I really want to keep all my symmetries of the problems, right? Because if I do a calculation that breaks gauge invariance, yeah, I might get some divergences, but these aren't physical objects, right? And so we should be doing a computation that respects all of the symmetries of our problem. Okay, so how do we do that? Well, that means we have to keep every term in the Taylor series, right? We actually have to see the entire sign. So what this means is, okay, so let's be slightly more explicit. In particular, the term that is normally divergent is mass. But we should again say we should Taylor series in phi. So we should be including the Taylor series that has one scalar. We should be including the Taylor series that has two scalars plus three scalars, etc. Plus dot, 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 right? Or we could try to just do the whole sign at the same time. But it's easier just to calculate diagrams, so that's the way I'm going to do it. Okay. So let's try to go through and calculate this. Okay. So what I'm going to do, you see there's basically two mass insertions there. So there's one mass insertion, which is whatever, y, f, and I'm even going to write sine a little bit differently because exponentials are easier than sines and cosines. So it's going to be e to the I phi over f minus e to the minus I phi over f times whatever, some number here. The main point is going to be showing that the answer is not infinite. So I'm going to be dropping some order 1 numbers. And what do we do when we calculate the potential or effective potential? We take phi equal to phi naught plus delta phi. We Taylor series, this is the background field method for calculating the effective potential. You Taylor series in delta phi over delta phi, and those are the propagators there. Okay. Great, and what we want is how does the effective potential V depend on your background value phi naught, right? We want V of phi naught. That's our goal. Okay, so we have two insertions there. One, let's say here, one, let's say here. What are we interested in? This guy, let's say, is position. This has location, position equals 0. And let's say this guy has position equal to x. And okay, I don't know, well, whatever. Let's say it's position equal to y. So x's are just mass insertions. Okay, so this has an e to the I phi naught over f. It has an e to the minus I phi naught over f. Same thing here. I phi naught over f e to the minus I phi naught over f. And remember, phi naughts are position independent. This is a background. And so if I want the potential to depend on phi naught, I either choose this piece or I choose this piece, right? So I'm just going to take this piece and then add its summation conjugate. Okay. So all right. So the effective potential is integral d4y. I have a fermion propagator here. If you haven't worked in position space, always done in momentum space, it's good for the soul to work in position space at least some point in time. So this is just going to be some fermion propagator taking you from 0 to y. This is squared. We're going to be taking a trace of it. Trace gives factors of like 4 and whatnot that we're uninterested in. So there's the propagator taking you from 0 to y, and then y back to 0. So maybe I should have written this as a fermion propagator from 0 to y, and fermion propagator from y to 0. And then, look here, I have e to the I delta phi at 0 over f, and e to the I delta phi at y over f. And I'm going to do all the Wick contractions here. Wick contractions to get my propagators. In other words, Wick contraction is what gives us all of that thing, right? When you Taylor series this, contract it, that's what I get. So let's go through here. There's going to be some order 1 numbers. I'm actually going to have to be careful with the order 1 numbers on the Wick contraction because it actually will matter. So, okay. All right. So I Taylor series these guys. So this is the Wick piece. I have Taylor series of an exponential is what? 1 over n factorial I phi of 0 over f delta to the nth power n and m. The second guy is 1 over m factorial I delta phi of y over f to the nth power. Okay. Great. We're just going to now start doing contractions. Well, if this has 3 of these guys, right, or let's say 1, delta phi of 0, delta phi y, delta phi y, like that, you can't contract enough to here, right? Notice you always have 1 on the left, 1 on the right. So you need to actually, you can't contract these guys properly. You actually need the same, you need n equals to m. So first thing, this is equal to 0 unless n equals to n. N, 1 over n factorial, I over f to the n. We're going to have a delta phi of 0 to the nth power. This is also 1 over n factorial, I over f to the n. And delta phi of y to the nth power. Okay. I can now contract these 2 guys, right? How many ways of contracting these guys with these guys are there? The first one has n choices. The second one has n plus minus 1 choices. The third guy has n minus 2, n minus 3, dot, dot, dot. And this is n factorial combinations. So this is the combinatorics. So what do we get? Okay, so we have the Wick contraction stuff is 1 over n factorial squared. I squared is minus 1 over f squared to the n. We have an n factorial, and we have n contractions of x to the nth power. This is a scalar. Okay. And now we have, notice that this is, sum is an exponential, right? It's a 1 over n factorial stuff to the nth power. So this is equal to e to the minus 1 over f squared times d of x. So all of these diagrams that I guess I just erased, when you add them all together, they add up to this exponential. And do I have, oh, I have it over here, great. So we can now write down what it is that the Coleman-Weinberg calculation is now that we've kept all the symmetries of the problem. This is, that should be y, I guess, not x up there. Let's just change it real quick. This is y, this is y. Okay, we have an integral d4y. If you haven't seen propagators in position space, I suggest you Fourier transform the more familiar results at some point. This is just 1 over y. Well, there's no mass in the problem, and so it's sort of dimensional analysis does it for you. This is a fermion, so fermion squared has dimension 3. Propagator, square it, so it has dimension 6. So this is over y to the 6th times some order 1 number. Scalar propagator is expectation value of 2 scalars, right? Dimensional analysis means it's 1 over y squared. Turns out the sign matters, so I'm going to tell you the sign is positive. Times some 16 pi squared, whatever, that's not particularly important. And so what do we have here? We have an integral, let's call y squared your distance, d. No, I have capital D, because I have an integral. So I have integral d capital D over d squared e to the minus 1 over d. And let's find, I guess I can get units right. If you want to get units right, you can do that with some order number. So clearly, if you ignore the exponential, right, that's what you do normally. You just say, don't deal with all these diagrams. Ignore the exponential. This is an integral of 1 over d squared. That is divergent, right? As d, this by itself, bad as your distance goes to 0 or momentum goes to infinity, right? Your UV cutoff. This is saying it has bad UV behavior. What happens when you put in this exponential? Now it has good d goes to 0 behavior, right? Because e to the 1 over 0 is infinity. So e to the minus infinity beats out any polynomial divergence you have here. And so you actually just get a finite answer here. Finite. So the mass of the scalar in our Yukawa coupled theory, if you just have sign coupling instead of just a linear term, you get a finite answer. And okay. So what does that mean? This also tells us why the scale f is important, right? We had said dimensional analysis, right? We took a theory with sine. Let's just write f sine phi over f times psi bar psi. We calculated a correction, delta m phi is, I'm not giving the order 1 number, but dimensional analysis tells you if it's finite, the only thing you can put there is f, and that is what you get, right? This 1 over f squared here is what makes this guy finite with dimensional analysis of f. And so we had guessed dimensional analysis scale is m phi over Yukawa coupling, which gives you f. And you ask, what happens at the scale f? Well, what happens at the scale f is, well, you can just ask here. What happens when you get to Yukawa's, or sorry, not Yukawa's, distances 1 over f? Well, higher order terms in the exponential are important, right? This is saying, as I get to, this is perhaps an unintuitive, weird situation where as I go to an energy or distance scale, let's say 10f, the exponential is e to the minus 1 over, well, e to the minus, let's say, if my energy is 10f, 1 over, this is 1 over 10f, the distance squared is this thing squared. Y was also a bad choice. Oh, God. Okay, let's call D. Go back to capital D. This is distances of 1 over 10f squared. And so, okay, up to some order of number, maybe this is e to the minus 5, right? What happens when you Taylor series e to the minus 1 over 5? 1 minus 5 plus 25 over 2 factorial plus 125 over 3 factorial minus plus, I probably should have gone all the way up to 5 factorial. Minus 5 to the 4th, 4 factorial plus minus 5 to the 5th over 5 factorial plus dot, dot, dot. And so let's just numerically evaluate this. What you see is these terms unimportant. These terms cancel a lot, right? E to the minus 5 is a small number. Everything here is large. And so this is saying huge cancellations. In, roughly speaking, the first 5 Taylor series terms. Okay, probably some order 1 number closer to 10 or whatever. But afterwards, when you have like minus 5 to the 10th over 10 factorial, this 10 factorial is huge, and so you're getting a very small number. Okay, maybe let's do 100 to make it even more obvious, right? And so these higher order terms are unimportant, but these first 5, 10 guys are important, meaning that the first 1, 2, this is 1 loop, 0 loop, or 0 additional loops, 1 loop, 2, 3, 4, 5. Actually, the thing that's most important is something like a 5-loop diagram. And then after you go to 6, 7, 8, it starts becoming small again. So you have a weird situation where perturbation theory is still okay, but only asymptotically. To get the right answer, you have to include like the first 8 terms in perturbation theory. So this is saying perturbation theory looks like that in terms of number of loops. Very weird, but this is actually just what your theory gives you. It's a little surprising. In fact, you can be like, does this really make sense? Should it be the case that a 2-loop, 3-loop diagram is more important? And you can ask, well, actually, yes, because you can ask, how did I get to this situation in the UV theory, right? The UV theory, the sine or cosine is really phi to the n times psi bar psi. And so if you want to do any loop diagram in the UV theory, I have a large number of loops, right? Plus HC, I guess. Right, the proper Coleman-Weinberg one-loop calculation involves n of these guys, right? And so what's happening is just perturbation theory is slowly itching towards getting n of these guys and intermediate states. So it's not actually too surprising once you know the full UV theory, because the full UV theory, this is a huge higher dimensional operator I'm talking about. And so it involves a lot of particles and a lot of loops. And so turns out even this is not super surprising. This is exactly what's true in the full UV theory, because literally you cannot write something without less than n loops. For the UV theory is even more. It's 0, then jumps up at n. Okay, so suffice it to say, we have essentially just, let's summarize it, because I think this is roughly all I wanted to talk about for naturalness. What are the 3 things that are important to get any model of the electroweak hierarchy problem to work? Order 1 numbers have to be in our favor. And I showed that, fine, maybe famous models like supersymmetry, order 1 numbers are not in our favor. But there are plenty of examples where order 1 numbers are in our favor, rather than the U1 in extra dimensions. There's the G-2 from NEMA. You could get it parametrically wrong when you say things, let's say, like the Zn symmetry. And 2, what happens at the scale? Well, what happens at this scale? What happens at the scale f is right when you have to start including 1, 2-loop, 3-loop, 4-loop diagrams. And so this is just saying it could be new particles. That's what it is in supersymmetry. But it could also just be new dynamics. Right there. This is just an explicit example where what happens at dimensional analysis scale is new dynamics, not new particles. And so new dynamics turns out to be very hard to look for, right? Because calculating cross sections and things like this are pretty difficult at the LHC. And so this is a lot easier to hide than new particles. And then I guess there's the final bit, which was what I talked about for the last lecture and maybe a bit before it, which is just different ways to evade dimensional analysis. Okay, any questions? This is basically what I was planning to talk about, the electroweak hierarchy problem. Speak now or forever hold your peace. So right now, this, I think it's not obvious. So what is it, why is it difficult? If you write just a non-abelian version of this, what goes wrong? If you just write Q, H, U, and you just change it to sine, Q, sine Higgs times U, which you can just define this by the Taylor series so that it's nice and well behaved in terms of SU2. The resummation, the n factorials aren't nice. I think what happens is you get a hypergeometric function, which is also an exponential suppression. But I'm not 100% sure. And so I think the statement I can make is that if you use this to calculate the mass term, just delta m squared, you get the same sort of behavior. That dimensional analysis is of order y squared f squared. Now, do I have a UV completion that gives this? No. So that's the hard part. But just at the level of an EFT, there's just no hierarchy problem or anything at this level. The other difficulty, which I guess I didn't really say here, is just ask, how does perturbation theory work? If, as I take this f and make it larger and larger, what is the UV cutoff of the scale? Because it's higher dimensional operator, it's going to have a UV cutoff. And the UV cutoff turns out to be this is where unitarity breaks down. So a lot more solid than anything else. 4 pi f times log the Yukawa coupling. So if you really want to separate the UV cutoff from 4 pi f, you also need small Yukawa couplings. And so top Yukawa is not all that small. And then order 1 numbers are important. And then it's kind of a complete mess. Yeah. All right, any other questions? Oh yeah. Yep. As in, why is it, so you're just saying, why did we guess new dynamics? Like what mechanistically made us guess this? And so what happened was we did dimensional analysis, assuming that this was the only diagram important in the story. And so so if you do that, then you get the scale f. But the scale f is also exactly when this is not the most important diagram in the story. You have to add another one, or another one, or another one. And so then you have to change how you do dimensional analysis, because suddenly something else is more important, right? If you do dimensional analysis with the hyperfine splitting, but then you suddenly find the Zeeman splitting is larger, you should switch over and do dimensional analysis for the Zeeman splitting. And so that's sort of the same thing is happening here, is you discover that's exactly the scale where I should be doing a different estimate. Yeah. Yep. So what happens if this is more important than that? This means that if you cut this diagram, it looks like if you scatter 2 fermions, you prefer to produce 4 scalars rather than 1 scalar. So to 0th order, you would just say, you start producing a lot of Higgses. It's like 2 Higgs production becomes more important than 1 Higgs, and then eventually 3 Higgs, 4 Higgs. Yeah, and so it's not entirely, you never see these loops. These loops themselves are impossible, but you can see their cut versions. And those are a lot sort of more in your face. Of course, why might it be hard for the Higgs? The Higgs, this is the top loop, and we don't scatter top particles. So it's going to be a little bit harder, but that's sort of morally speaking what it is. It's just you start producing more and more Higgses. Yeah. All right. If there are no further questions, then I guess we'll head off the break, and then when we come back, I'll do a very brief discussion of the strong CP problem. Okay, everyone. Let's get started. Actually, there is an iPad pencil here. Someone probably, okay. It was in the chalk. So someone should find out. Well, I guess now if you think it's yours, go talk to him. So not my problem anymore. Okay, so Great, we're now gonna move on to the last sort of naturalness problem that people will talk about. So this is the strong CP problem. So we only have a little bit of time, so let's see how much we can get in. So let's do a very brief overview of what it is. And to do that, I can actually just go back to, so let's do it classically and then we'll do it quantum mechanically. So classically, the question is, what is the neutron EDM? Neutron, EDM of neutron. So what you can do is just walk up to an undergraduate and ask them to draw you a picture of a neutron. Tell them it's made of an up quark and 2 down quarks. Up, down, down. And calculate, then tell them plus 2/3, minus 1/3, minus 1/3. What is the EDM of it? And you get something that is very much not equal to 0. What we've done is measured the EDM of the neutron, or rather, we tried to measure it, and we found 0, at least experimentally consistent with 0. And so the statement is actually, they drew this wrong. This angle should be 180 degrees. And so this is the proper way to draw a neutron. If you're gonna pretend it's a classical object, draw it as a straight line so that you get its classical dipole moment correct. And so the question is, why is this the correct picture of the neutron? When, unlike carbon dioxide, if you bend a neutron, it stays bent, right? There's no reason that this thing can push itself out or anything like this. So this is basically just the question of the classical strong CP problem, which is the neutron dipole moment has no reason to be 0. And for some reason, we've measured it to be absolutely tiny. That angle there has to be 180 degrees within about 10 to the 12 degrees. So quite small, or 10 to the minus 12 radians. But okay, so quantum mechanically, let's phrase the problem again. So what is the problem in quantum mechanics? The quantum, it's going to be the exact same thing. That's an N, quantum. Okay, so the statement is my Lagrangian for the neutron and everyone involved involves the kinetic terms, involves a mass term for the up quark, u bar u, plus md e to the I theta d d bar d. So mass term for the, actually I was doing conjugates notation, so uu conjugate dd conjugate. Okay, so there are mass terms, right? But we're EFT people. We write down every term consistent with the symmetry of our problem. And so we could write down a term plus theta over 32 pi squared gg tilde. Okay. So the question is, what are the physical consequences of theta, theta u, and theta d? Now, this QCD turns out to be very, very difficult. Trying to calculate what happens at low energies is impossible unless you're a lattice person, and then they could actually just put this on the lattice and see what happens. However, I'm a theorist. Someone can tell me a computer spits out this answer, doesn't teach me much, right? I don't care about the answer, I care about how I got there. And so let's see how far can we get with just a single input. So we can take this either from lattice or from experimental consequences of QCD. But through one of those two, we know that quark conjugate is not equal to 0. So what does this mean in terms of symmetry structures? So what is the symmetries of our theory? Because if I see stuff turning non-zero, I have Goldstone's theorem, right? Goldstone's theorem is just a full theorem. There's nothing you can do about it. Doesn't matter if you have strong coupling, weak coupling. It's just a true statement. So let's write down our symmetries of our problem. And I did not give myself enough space. Okay, so I have, let's see, my quarks, quark conjugates. I'm going to write them as a doublet. There is going to be SU3 color. This is a fundamental. This is an anti-fundamental. And then I guess have my mass matrix spurion equals mu e to the I theta u 0, 0, md e to the I theta d. It has no SU. You have SU2 left, which rotates this guy. This guy transforms as an anti-fundamental, since I can write this mass term as, if I want to write fundamentals as like this, UD. And then I have a matrix, mu, md, u conjugate, d conjugate, e to the blah, e to the blah. So this transforms here, this transforms opposite. We have SU2 right. I'm just going to bar it to show that it's vector like, what is that? That's a column, row vector. And this, I have U1 baryon number. So this is 1 minus 1, 0. And U1 axial, which is 1, 1, minus 2. Okay. Turns out this is an anomalous symmetry. So I also need to take theta here and say under U1a, theta goes to theta, what is it, plus or minus 2 alpha. I think it's minus 2 alpha. Minus 2 alpha. Okay, so these are all of the symmetries of my problem. And great. Now, what do? I say QQ conjugate is non-zero. So what does this break? What does Q and Q conjugate break? Breaks SU2 left, breaks SU2 right, and it breaks U1 axial. Down to the diagonal. SU2 diagonal. So when left equals right, this is. So in particular, this is equal to 1, 1, 0, 0 times whatever, 100 MeV to the 4 cubed with some, maybe a 4 pi out here or something like that. Sometimes their GeV appears, sometimes 100 MeV appears when you're talking about pion stuff, or QCD. Okay. So I have broken one SU2 and one U1A. And so I should have 4 Goldstone bosons. Okay. 4 Goldstone bosons. Stone bosons. Okay. So what do? First I say, how do I parameterize these Goldstone bosons? If you recall, it's actually a part of Goldstone's theorem. It also tells you how to talk about them, which is you take your vacuum and you just perform a broken rotation. Perform a rotation broken transformation with alpha equal to your pions, pion positions, and that gives you everything. Okay, I'm going to call, just because it's the 3 from SU2, I'm going to call pions pi. The 1 from U1A, I'm going to call the eta prime. This is just notational thing, but okay. How does that mean? I do a transformation, Q conjugate. Okay. There must be a way not to constantly break these things. E to the I pi a ta times my identity matrix times e to the I pi a ta. Usually, right, this thing just becomes the same thing squared, and then at some point people have to choose normalizations. I'm going to call this U, and there are a lot of different conventions for dealing with how to define things like the pion decay constant. Just the one I'm going to choose here is e to the I pi a ta for square root of 2 f pi, where pi a ta is pi 0 minus pi 0, pi 1 plus I pi 2. I might have minus I pi 2. They have trace of a half. So I guess there's over square roots of 2 here. And then plus eta prime, plus eta prime. Okay, I might have gotten sigma y wrong, so there might be a minus sign here, but it's polyspin matrices plus the diagonal. Great. So we have how to talk about our pions. We have the spurions here, m and theta, right? So if m and theta, if these spurions did not exist, then you'd have a bunch of massless Goldstone bosons. But they do exist, and so we just write everything consistent with symmetries. So let's write everything consistent with symmetries, because we're effective field theorists. This is how we do things. Okay. First, trace du dagger. So there's the kinetic term, and with my normalizations, this is f pi squared. And if you Taylor series this out, you see that one of the leading order terms, or the leading order terms, is d mu pi I squared 1/2 sum over I. So I have canonically normalized kinetic terms for the pions. Excellent. There's an order 1 chance that this has no square root of 2. I was just trying to do the math in my head, and I was not getting all the factors of 2 working out. This is what I get for writing stuff not in my notes, but oh well. Okay, so up to possible factors of 2 and square roots of 2. This is right. If you decide to trust that, you might put 2 or something else here. Okay. And in fact, this tells us a lot more. It tells us things like, this term also tells us pi d pi squared, etc. And so this actually contains a lot of information. Basically, we measure one thing, f pi, and we can get tons of stuff about the pions. And they actually even are borne out by experiment. However, at this point, we have not written anything using our spurions. So we're going to have to start writing how do things transform. So for example, Q times Q conjugate transforms as box bar. So fundamental under left, anti-fundamental under right. So we can write an additional term, which is constant times trace of m times u. And in fact, let's put f pi cubed here to get the order 1 numbers. Okay. So this, you can ask plus hc, gets the mass of the pions. And we can Taylor series this. Did I write down what they were? No, I did not. Okay. What you get is, for example, things like m of the pion equals m pi plus minus is something like mu plus md times this f pi times the constant. And so because of the constant, well, what do we see? Out of this, we can see if the quark masses were 0, then these SU2 left, SU2 right are real symmetries. And so you get real Goldstone bosons. So the mass goes to 0. That's great. However, we have a constant that we can't calculate. Okay, unfortunate. But this does tell us, for example, that to leading order, the mass of the pion should be equal to the mass of the charged pion. The charged and neutral guys should have the same mass, which is what we observe. They are approximately equal to this order in the computation. Okay, and I think if I include the eta, it also appears here. Okay. And I wrote something dimension 2, so I guess these are squared. Okay, so that was using the spurion m. Let's continue to write things with the spurion theta now. So first things first, notice this also preserves the U1 axial rotation. This rotates by 2. This rotates by minus 2. So that's good, right? U goes to e to the 2I alpha times u under the U1 axial. However, now we want to say, let's try to use this somehow or another. So let's construct, you'll notice, e to the I theta times u goes to e to the I theta times u under the U1 axial. So anything I can write that involves this is fair game. Okay, but notice this still transforms under left and right. So we're going to have to get rid of left and right. So it turns out these are special unitary matrices. So their determinants are a nice way to get rid of any transformation property. So we can write down a term, determinant e to the I theta times u, right? If you do an SU3 or SU2 left, SU2 right transformation here, this gives a u left, u right. One of those is daggered. The determinant, which is equal to the determinant of u, because determinants are the determinant of each of these guys individually. This is 1, this is 1. U is not 1. So let's take the determinant of u here. Determinant of u is e to the I eta, maybe with a 2 there. I'm not being super careful with 2s. Okay, maybe with an order 1 number there. Okay, great. So we have something in our Lagrangian that we can add. What is the effect of this term? Eta was the U1, the Goldstone boson of U1A. Oh, it should be eta prime. There you go. And so we have a term in the Lagrangian, which is e to the I theta plus eta prime over f eta prime times some number, whatever, f pi to the fourth times some number plus Hermitian conjugate, which is, if you Taylor series this, you get something like theta plus f eta prime over prime squared f pi to the fourth times some number. Okay. So we get some mass term for the eta prime. M eta prime squared is whatever, f pi squared, f pi to the fourth over f eta prime squared times some number. Okay, so we see the effect of the theta angle is that there's a mass term for eta prime and that the vev of the eta prime is equal to minus the theta angle. Maybe with some order 1 numbers there because I was being a bit sloppy. Okay. Great. In the end, we still want to calculate some physical effect of theta here. So notice the following, which is this is a statement about nature. Yeah, which is that, sorry, I was not meaning theta, which is mu, md are very small. Notice the mass of the eta prime is large, right? There are no quark masses appearing here. It is a large thing, and so I might as well just integrate it out and set it to its vev. So after integrating out and I probably had a minus sign error somewhere compared to my notes. Oh well. Okay, so integrate out eta prime. In other words, just set it to its vev, eta prime to vev. And then continue on and just study the theory of pions, pi plus, pi minus. Okay. What does this mean? U is E. Turns out, I guess in my notes I wrote it as this, e to the I pi a ta over f pi. So up to order 1 factors, you just get e to the I theta there. Okay. And as before, we're going to just start doing things, let's say, like calculating the pion masses. Great. Whoops. I can take this, plug it into that guy up there, into here, and calculate the mass, right? I don't Taylor series in eta prime anymore. I can just calculate the mass term here. Okay. So take that, plug it into trace mu times some numbers, and proceed. What you get is, okay, so there's two steps for proceeding here. The first is we want to calculate if the pions get a VEV. So in other words, is pi plus or minus equal to 0 and pi 0 equal to 0. Turns out this would break E and M. This is actually just minimize this guy with respect to VEVs. This is actually not equal to 0. You minimize this, and so okay, let's super quickly just sketch what that looks like. You get some number, trace mu e to the I theta u, md e to the I theta d, 0, 0. So u1 factor, there's an e to the I theta over 2, and then e to the I pion is not equal to 0. E to the I, let's call VEV of pi 0 over f pi, e to the minus I, VEV of pi 0 over f pi, like that. Plus Hermitian conjugate. Okay. Plus HC just turns things into sines and cosines. First term involves mu cosine theta u plus theta over 2. There is, okay, so somehow I claim that I got the order 1 numbers right. Plus VEV of pi 0 over f pi. And plus md cosine theta d plus theta over 2 minus the VEV of pi 0 over f pi. Okay, take a derivative, set it equal to 0. We know what's the VEV of pi 0. It's a bit of a mess. We find tangent of the VEV of pi 0 over f pi equals mu minus md over mu plus md. Tangent of theta plus theta u plus theta d. Okay, so this combination is sometimes theta bar, and this is going to be the parameter that turns out to be very small. Okay. So, great. You can even do things now, calculate the pion masses, and pi squared. It's going to be some god-awful mess. Do I remember it? No. It is. Okay, let's just. If nothing else, you can just plug this back in and get the vacuum energy of your theory. I'm just going to write the vacuum energy of your theory. Square root 1 minus 4 mu md squared sine theta bar squared. Is that theta bar over 2? I feel like it probably is. Over 2 with a minus sign. Okay. So we have found at least one physical effect of theta bar is the vacuum energy of your theory depends on it. It turns out there are plenty of other things that depend on theta bar here. So for example, I could Taylor series this and calculate the pion masses now. So my pion masses, so normally it's the normal value, but it's a mu squared plus md minus plus, oh, it's minus or plus? It's plus 2 mu md cosine theta, for example. So you discover the pion masses depend on it. You can even do a one loop calculation. If this is the neutron, pi plus minus, radiate off a photon. Go through, calculate this again, and you get the electric dipole moment of the neutron is proportional to theta bar. Probably sine theta bar, but sine. And so you see, as advertised, neutron dipole moment depends on this theta bar. And it turns out experimental constraints on the dipole moment of neutron, well, technically, experimental constraints on the dipole moment of mercury, and then some nuclear people tell us how that turns into the dipole of your neutron and proton, imply theta bar is less than 10 to the minus 10 or so. Okay, so there's a term you could just write in your Lagrangian, phases of the quarks, theta, whatever it is, and their sum has to be small. And so this is the strong CP problem. Why is this number, which could have been anything in the world, right, any number between 0 and 2 pi, happen to be extremely close to 0? Okay, so let's, as before, go over some of the solutions to this thing. Do people have any questions on it so far before sort of just establishing the problem? Yeah. Ah, excellent. So let's say, okay, for this guy here, just to show that it's at least depends is non-zero. This won't tell you the answer what its value is, but at least show it's non-zero. Yeah, so, oh, y is plus or minus non-zero, or 0. Ah, okay. So if you want to do that, let's see. So, well, here's the easiest thing. So if pi plus or minus the VEV, let's call it just V, this will give a mass to the photon, which is E times V. And so this is going to be, let's see, Lagrangian. So for example, let's say we take the Coleman-Weinberg potential for the photon. This is going to be ma to the 4th. Turns out it's a plus sign. And so this is e to the 4th times the VEV of pi plus or minus to the 4th. And so it's true that a lot of these other terms actually don't really tell you a whole lot about the pi plus pi minus. It's when you put in E and M that it really nails it to 0. So it's all about E and M to set pi plus pi minus to 0. Yeah. Okay. Okay. Solutions to the problem. Simplest one is solutions is if mu equals 0. Right? So if mu equals 0, this implies theta u ill-defined, which means theta bar is ill-defined, and so there should not be any question. No, there should not be any issues, right? This is another way of saying, secretly, if I did all of these computations, look, set mu equal to 0, oh, the pion mass no longer depends on theta. Set mu equal to 0, oh, vacuum energy does not depend on theta. Do this calculation. You will find an mu out front. And so the mu equals 0 limit is just saying theta u is ill-defined. The whole point is, what is this combination, which involves theta plus theta u plus theta d. And if one of those guys is ill-defined, then clearly your answer cannot depend on that combination. Okay, at this point, you go to your lattice friends, say, calculate everything when theta equals 0, when theta equals not 0, et cetera, et cetera. What is the value of mu? They come back and tell you that at 10 sigma, they think that mu is non-zero. So, great idea. Lattice people tell us that it's wrong. Okay. Great, or maybe not so great. Really don't have time to talk about stuff. And so I'm gonna definitely, second attempt is we're gonna find a relaxation solution to the problem. Okay, so is there a relaxation solution? Well, remember what we said when talking about relaxation. 1, make xxx a function of a field. I guess let's call it phi over, we're going to call it the axion, A over F. And then 2, make xx equals 0 a minimum energy. Okay, so let's look at number 2. Oh, I didn't even erase it. Excellent. Energy as a function of theta bar here. So let's plot it. V as a function of theta bar. And this is a minus sign. We want this thing to be as large as possible. So we want this to be 0. So in other words, this is theta equals 0. Theta bar equals 0 is min. So in other words, we need to do absolutely 0 work to make a relaxation solution work, because standard model automatically sets theta bar equals 0 to minimum. Okay. Next, make theta depend on a field. Make theta bar actually something that can change. And so there are plenty of ways to do this. Right, we had our Lagrangian, theta over 32 pi squared. I don't know why I even wrote the 32 pi squared, since order 1 numbers I'm not being careful about. Theta u conjugate plus md e to the I theta d dd conjugate. And so I have to just do one thing, make one of these fields, or add a particle that couples like one of these fields. So I could do, for example, plus a over f, 1 over 32 pi squared gg tilde. Then theta bar, which equals theta plus theta u plus theta d. Well, this couples exactly like theta, so you do plus a over f. And so this is the axion solution, is you write one new field, A, and you write one new coupling. So I'll even write the kinetic term. This is literally all you change the Lagrangian by to solve the strong CP problem. I added one coupling and a kinetic term. So one field with one coupling. That's all I needed. I could add other stuff. In fact, other stuff will be generated by RG evolution and all that annoying nonsense. But in principle, all I have to do is one field, one coupling, relaxation mechanism automatically works. So you'll notice how easy this was to implement. And this is why if anyone talks about the strong CP problem, the Axion solution, which is a relaxation solution, is the first thing they will talk about, and usually that's what they'll stop to. They don't like other models because it's really hard to beat one field, one coupling, right? Admittedly, it's non-renormalizable, so once I UV complete this, it'll have a whole hell of a lot of couplings, but at this stage, there's, as an EFT, it's absolutely beautiful. Okay, so let's talk a little bit. Do I want to talk about other stuff? Let's talk a little bit about the opportunities here, and they're basically only not a huge lot of them. So one, notice to get this thing to work, we needed this to be the only coupling you write. So in other words, this is the only potential we need. So if you decide to write cosine A centered around 0 instead of theta bar with maybe some, let's write GeV to the 4th or something, then the minimum is no longer at theta bar equals 0, right? I added another potential which competes against this. There's going to be some minimum, which is some combination. And so the question is, how to prevent this? Okay, so this is called the Axion quality problem. And it is annoying in the sense of, well, there's no symmetry that forces this to be the only coupling of A. And so I could write a whole ton of other stuff. And when people come to Axion model building in terms of solving the strong CP problem, this is the only problem they talk about. There's basically nothing else that really comes to mind in terms of, let's see, I can even look at my notes. Yeah. In terms of the Axion, at least, this is the only one, and there are a lot of solutions to this, right? So there's a lot of solutions, and so this is part of the reason why the Axion is popular, is in terms of problems, and I guess, unfortunately, opportunities, there's basically only one problem that people have worked on. So what have people have done? They've gone off and created their own annoyances, which is to make it dark matter. Be like, this was too easy. Let's move on and try to do other things with it. So we try to make it dark matter. Also turns out to be an extremely well-solved problem. It is, turns out there are, if you want the names, there's two mechanisms that are pretty easy to do it. One is basically just assume the universe was hot and then let strings produce it. So their strings can produce it, and there's the misalignment mechanism. These are probably the two favorite ones, but there are a near infinite number of ways of making this thing dark matter. And so, again, people were like, okay, too easy. What else can we do? And now, the popular thing to do with axions is look for them. Designing an experiment, becoming an experimentalist. So design an experiment to look for them. 3, design and experiment to look for axions. Where did I put? Oh, I just, it could be anything. It could be m Planck to the fourth, whatever. I just chose a random number. And in fact, if you want it not to be a problem, it should be smaller than 10 to the minus 10. It should be smaller than this. Smaller. Yeah. Okay. So I'd say with the axion, these are the three things. It turns out at this stage, it's actually also quite difficult. And so people have gone back and just assumed it's dark matter and then look. And so I only have to detect it. I don't need to produce it as well. But there are plenty of ways of doing things these days. So if you ask, where is most of the progress with axions these days? It's on this side. All right, so I'm basically out of time. All I have to say is there also exist parity solutions, parity, and charge parity solutions as well. These are not quite as popular, but at least parity, there's some nice models that do it pretty well. I would tell you if I had time, but I don't. Charge parity, CP, tend to be a bit uglier, but I would say at least the minimal parity model is quite nice. And so I encourage people to at least look that one up. All right. Any questions? It was a very lightning fast thing through strong CP since I ran out of time, but sorry about that. Okay, everyone is in a hurry to get off and relax for the weekend. So I will see you guys later then.